This is Bipin Bhaskar here. Today I am going to present you a series of video lectures on the introduction of thermodynamics. These are a series of video lectures for enabling easy understanding of thermodynamics. The inspiration for these videos came from the classes that I take and the difficulties I observed in the students. The language used is simple and supple, and it is hoped that these video lectures will enable you to master the subject of thermodynamics. Kindly note that I do not endorse my videos to be better than any of the other prominent professors out there. I also learned the concepts by following the video lectures of many other professors. But a small thing which I observed is that much of the videos which are out there are presented in much more rigorous fashion, which a student who is in the very introductory stage find it difficult to understand. So the only purpose of my video lecture is to play the role as a bridging block, so that once you understand this, you will be able to master those books as well as the videos out there. And I also endorse the copyright of the images and the animations that are used to the original artists who created them. So let's begin with, what is thermodynamics? Thermodynamics is that branch of science that studies matter and energy, interaction between matter and energy, and the effects on the properties of the matter due to energy interaction. As an engineering subject, one must be aware that thermodynamics plays a very fundamental role. This is because in engineering we come across various types of machineries, equipments. For example, let's take internal combustion engine. In internal combustion engine, the fuel is passed into the engine, the stroke takes place, and the combustion of the fuel takes place, and at the end of the stroke we get a power output. So in a very small way, if you observe this, there is a flow of fuel into the engine, there is some work done on the engine, some chemical change, phase change happening in the fuel, as a result of which the work output happens. So there is actually an energy interaction. Now, why should we study thermodynamics? In this universe that is chiefly made from matter and energy, we can see constant interaction between the matter and energy. And there are such subjects in engineering as internal combustion engine, the heat and mass transfer, power plant engineering, heating, ventilation, air conditioning, refrigeration, etc. All these come as a direct consequence of thermodynamics. Thermodynamics plays an important role in design as well. Example, the design of the thermal insulation, air conditioners, heaters, etc. When we are studying thermodynamics, it must be kept in mind that thermodynamics is just not a theoretical subject. It is actually a subject that has direct consequence in designing. For example, we have the radiator designing, the fins designing for proper heat transfer in the engines, the chiller plant or the coolers, etc. So in thermodynamics we study about the fundamental aspects that govern the energy interaction in this universe, and like any other subjects, thermodynamics is a natural subject that is based on experimental observations of the phenomenon that happens in this nature. And these experimental observations are condensed into the theories that form the foundation of thermodynamics as well as other allied subjects. So if we master these basic things that form a part of the thermodynamics, it will be very easy to understand all other daughter subjects like internal combustion engine, power plant engineering, etc. So let's begin with the study of the first law of thermodynamics. The first and the basic aspect about the universe as an intelligent human, which we must be aware of, is that energy in this universe is conserved. Unless and until destruction of matter takes place, no new energy is created. And this is what Albert Einstein proposed to his theory of relativity. When a matter is destroyed, an equivalent amount of energy is created, and if energy is eliminated, equivalent amount of mass should occur somewhere. That is, mass and energy are interconnected with each other and both are conserved. So the students are advised to refer to any other relevant literature on theory of relativity for further understanding as well as a deeper understanding of the phenomenon. We have been learning since our smaller classes the law of conservation of energy, which can be stated as energy can neither be created nor be destroyed in an ordinary process. It can only be transformed from one form to another, and the total energy content in the universe always remains balanced. There are myriad forms of energy out there, like we have mechanical energy, we have electrical energy, nuclear energy, chemical energy, light energy, sound energy, etc. But in thermodynamics, our focus will be only on the heat energy and the mechanical energy in the form of work. Now, the question that should come into our mind is why we are concerned only with heat and work. Why not any other forms of energy? This is actually the originating factor for thermodynamics, and understanding this, we will get to know why thermodynamics was created first of all. Long ago, when the human civilization was progressing, men constantly looked for those means that reduced his manual labor, saved time, and improved productivity. This led men to invent the machines. But with the invention of machines, there has been higher output, and man saw that he now has lot of such product more than what he actually needed. So now the quest become what to do with the excess of the outputs. This led to the beginning of trade and commerce, and rest as we know is history. So we will be not dealing with that. As time went by, trade flourished, technologies improved, people had more money, cities developed, lifestyle of the people improved. Then man came to such a stage that he demanded for a technology where the machine works on its own without human intervention. And this led to the challenge of finding a suitable source of power, because only human intervention apart from an intelligent machine is that we provide the mechanical power. For example, we will be rotating one of the shafts, so giving a suitable power, that was one of the need. So this quest resulted in man observing the amazing power of steam. Thus man's curiosity led him to study the properties of the steam and the means of producing steam. Now, how steam was produced then? Man discovered that when a fuel was burned, heat was released, which was used to boil the water. This resulted in increased kinetic energy of the steam, and this energy was used to provide the rotary power with the help of the turbines. Thus was formed the subject matter of thermodynamics. Hence, as an engineering subject, our focus is identifying and harnessing the various sources of energy, developing some means to convert this heat into some form of a usable mechanical work. Hence, we can observe that from the foregoing discussions that we have been listening so far, there are 4 factors that has been playing in the background. We are adding heat to something, we are removing heat from something, we are doing work on something, and we are obtaining work from something. So these are the 4 aspects in the thermodynamics that guide us in the background. And this something on which we are focusing our attention in thermodynamics is called a thermodynamic system. So now we will be trying to understand what is a thermodynamic system. A thermodynamic system is the quantity of the matter considered in isolation or as confined in a well-defined space on which we focus our attention and from which the energy interaction takes place. But a system cannot exchange energy in isolation. There should be something else that takes energy from the system and gives energy to the system. For example, let's consider the first part of the statement. It is any quantity of the matter that is considered in isolation. For example, I might be focusing the energy transfer that are taking place across the cell membrane in a plasmodium. So a plasmodium can be my system. I'm observing how much heat is transferred through the air conditioner. The air conditioner can be my system. How much heat is transferred by a boiling liquid. So that boiling liquid can be my system, or as confined in a well-defined space. For example, the fuel contained inside the piston cylinder arrangement, or the fluid which is expanding through the centrifugal pump, etc. So we can have either a system as a standalone or a system which is stored inside some other container. But the system on its own cannot exchange energy in isolation. There should be something else that takes energy from it, or something that can give energy to it. And the second component is called the surrounding. So let's look at the diagram. So as we can see, there's a system and a surrounding, and it is separated by a barrier as shown by the black color. And this dividing line that separates the system from the surrounding is called the boundary of the system. But utmost care must be taken while deciding the boundary, because it has been seen that an illogical choice results in paradoxical and hypothetical situation appearing true. For example, there are many students who used to ask me, like suppose a vehicle is traveling with certain speed, and what if we apply the brake? Can the braking energy be converted into some useful energy? Or yet another theory that most of the students come up with is that suppose the vehicle is running in its full RPM. Consider that we attach a dynamo to the rear axle, so that when the vehicle is being propelled by the energy of the vehicle, the same rotation energy will be equivalently converted into electricity, and it will keeping on charging the battery, as if they are creating a system that will perpetually create energy, and a device which forever runs without additional energy. Such perpetual motion machines, or you can say the hypothetical machines, are the result of illogical choices of the boundary. The boundary of the system does not include the metallic or the non-metallic walls of the container in which it is kept. This is because the boundary should not involve in any form of the heat transfer. The walls of the container, example the metallic walls, it has some thermal conductivity. So when the working fluid is in contact with the metallic container, it is actually transferring the heat to the metallic container. But this is contradictory to our definition that a system exchanges its energy only to its surrounding, not to the boundary. So the metallic wall forms a part of the surrounding. To help us resolve this dilemma, let us now discuss the concept of a working fluid. The working fluid is any liquid or gas or a vapor which is undergoing any physiochemical changes inside the container, and as a byproduct of such physiochemical changes, energy is exchanged. Thus, our thermodynamic system is actually this working fluid. The container only performs the role of storing the fluid. That is why the walls of the container does not form a part of the surrounding. Hence, if you look around in this universe, there are collections of such systems and surroundings. Hence, system plus surrounding together forms the universe. Now, let us delve into the mathematical concepts. As with any other science, thermodynamics also has its fair share of rigorous mathematical calculations. There are formulas and derivations, but these formulas and derivations are not made just for their mathematical beauty. Each symbol and the sign convention, whether it is positive or negative, has a physical meaning. One can master the soul of thermodynamics only if you are thoroughly aware of these sign conventions used. The second dilemma which I always observe in the students is that they make huge mistakes in these sign conventions, and even after going through various literatures, I also observed that there are two types of sign conventions that are used, and however only one of them is explained, and why the second sign convention came, nobody explained in the literature, as a result of which student makes confusions and they make the wrong answers and they get very poor results in thermodynamics. So as part of this video lecture, I would like to discuss these two sign conventions involved, and I am pretty sure after going through this you will not find thermodynamics difficult anymore, and I am pretty sure you will actually start enjoying thermodynamics. Now, the two sign conventions used in thermodynamics are sign conventions from the point of view of a scientist in thermodynamics. Let us now consider, if we are a researcher in thermodynamics, if we are delving deeper into the subject matter, what would our focus be on? Any interaction that results in the increase of the internal energy of the system is taken positive. Now, what is internal energy? Every object, every matter in this universe has some energy of its own. You can say this energy is the result of the molecules which are there or its natural state. So every system in its defined state has some internal energy. So if we are adding heat and if we are doing work, there will be an increase in the internal energy of the system. Hence, heat added to the system is positive, work done on the system is positive. Whereas if I am removing the heat from the system, or I am making the system do some work, there is a decrease in the internal energy. Hence, heat removed from the system is negative and work done by the system is negative. The standard symbols for heat in thermodynamics is Q, and for work it is W. Hence, heat added to the system is plus Q, heat removed or rejected by the system is minus Q, work done on the system is plus W, and work done by the system is minus W. Now, the second sign convention. Actually, the second sign convention is from the point of view of an engineer. The sign convention from the point of view of an engineer. The main focus of an engineer is designing a power producing system. Thus, power produced by a system is taken positive and power consumed by the system is taken negative. Thus, work output from a system is taken positive and work input to the system is taken as negative. Let us try to understand this in detail. As it was mentioned earlier in thermodynamics, we take either a liquid, vapor or a gas as the working fluid. Hence, our system will comprise a closed chamber with a movable system for the transfer of work and a conducting wall for the transfer of heat. Consider that a fluid is contained in the cylinder. Let the piston be given a displacement of L meter to the right, thereby compressing the fluid. Let us assume the area of the piston be A meter square. We know that pressure is given as force upon area. Also, work is defined as the product of force and displacement. Here the force is because of pressure, hence it is also called as pressure force. Thus work is pressure into area into length, but from elementary mathematics we know area into length is volume, hence work is pressure into volume. Let us now consider a differential work dW corresponding to a differential displacement dl. Therefore dW is equal to pdV. Also let us consider the system is moved from a state 1 to state 2. Thus the total work done in moving the system from state 1 to state 2 is given as W is equal to integral from 1 to 2 pdV. Also it can be seen that during the compression the volume of the system decreases, and during expansion the volume of the system increases. Thus compression work is given as minus pdV and expansion work is given as plus pdV. Hence in short, whenever you come across in the literature the term minus pdV, it is from the sense of the work input as given by a compressor or by the pump from the point of view of an engineer. Now since we are aware with the two sign conventions, let's review it in a shorter sense once more. If we are talking of change in the internal energy, then we should use the sign convention that heat input to the system is plus Q, heat output is minus Q, work input to the system is plus W, and work output from the system is minus W. Whereas if we are talking of a power producing system, for example an engine or a power plant, and we are talking of work done by the compressor or work done by a pump, here we will be talking using the term minus pdV. So I hope that these two sign conventions are now clear. Hence understanding these two sign conventions and the defining philosophies will enable to avoid the complications in the study of thermodynamics. In the next lecture we will be discussing more about what is a system, the different types of the systems and other elementary aspects, as well as the rigorous mathematical calculations and derivations of some of the equations, including the equations of ideal gas, etc. And if also possible, during these video lectures I will also be trying to discuss some numerical questions and explaining how to solve them using the various equations. Thank you.